Hi guys, in this video we're going to be going over a more detailed explanation of derivatives. So we're actually going to go into the definition of a derivative and we're going to look through some examples. So if you haven't watched the last video, part one was about mainly an introduction to derivatives and an introduction to slopes and understanding how slopes affect curved functions and how we can approximate the slope of a tangent at a point by calculating the slope of a local secant. So that's the basics. Now we're going to dive into the more fundamental definition of derivatives and some examples. So this is where we left off from the last video. So we left off from this paragraph, which says if we took the limit as h approaches 0 of the slope of the secant line between 2 points, a, f of a. So we have this graph here, and I have 2 points on it, a function, and I've graphed on it a function f of x, and I've marked 2 points, a comma f of a, that's that point right there, and a plus h comma f of a plus h, which is that point right there. And I'm saying if we took the limit as h approaches 0, so h is that increment in x, so these 2 points are away from each other by that h value. So if we took the limit as h approaches 0 of the slope of the secant line, so that's the dashed line is the secant line between those 2 points. If we took the slope of that and we took the limit as h approaches 0, so if we kept on reducing h, if we ask ourselves, well, what happens as h approaches 0? Will that slope approximate the slope of the tangent line at a? And indeed it will. And that tangent line is, well, it's actually not the exact, that secant line will never be a tangent line. Something to clarify, that secant line will never actually be a tangent line. It's always still going to be between 2 points, but it's going to be a good constant approximation for the slope of the tangent at x equals a. So this takes us to the derivative. The derivative. Okay. So the derivative. This is the idea of the derivative. D over dx, d of dx, and that's one notation for derivatives. That's Lagrange's notation, I believe, but there are other notations. So that the derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. And remember, this f of x plus h minus f of x over h, that's nothing but the slope. That's the same thing we got here when we were just going over the fundamentals of the slope. That's the same formula we got here. And that's the diagram for that formula. So that is the slope. This is nothing but the slope. And what we're asking ourselves is, well, what happens to the slope as h approaches 0? So as the distance between the 2 points decreases, what happens to the slope between those two, of the secant between those 2 points? That's the main idea of the derivative. Now that's a lot of fancy notation. So let's actually go through an example and use this tool to find the slope of the tangent to the graph f of x equals x squared at x equals 3. So I have the graph f of x equals x squared here. That's that curved function right there. And I've drawn and I've dotted the point 3, 9, which is on the graph. And I've also sketched the tangent line at 3. So the tangent line at 3 is the tangent line which only touches the graph at that single point. And we want to find the slope of that tangent line. That's the aim of the derivative. So I'm saying f prime of 3, and this is another notation for the derivative. So f prime of 3 is basically what we're telling the or what we're saying is that we're going to evaluate the slope of the tangent line of the function f of x at 3. So that we're basically saying we're evaluating the slope of this tangent line. That's f prime of 3. So we're saying that that's equal to, and we're using our derivative formula here, we're saying that's equal to the limit as h approaches 0 of f of 3 plus h minus f of 3 over h. So over here we have x here, and here we're just substituting 3 for x. Now, what does this statement really mean? Well, if we let me just extend this graph here, and I have another point, and it's kind of trivial, the spacing, and it's not very oh, the camera blurred. I did not want that to happen. Come on, unblur. Come on. Okay, there we go. All right, cool. So that point here, the x value of that point would be 3 plus h. That the x value of that point. And what we're saying here, that expression right there is nothing but the slope of the secant joining these 2 points. So if I had a secant intersecting those 2 points, that's that expression right there. That is what that is the slope of that secant line. And we're asking ourselves, as h becomes smaller and smaller, what is the limit as h approaches 0 of the slope? What does the slope approach? So well, f of x is equal to x squared, so we can literally just pop that function right here. F of 3 plus h is nothing but 3 plus h squared, and we're just evaluating that. So we have 3 plus h squared minus 3 squared over h, and what we're going to do is we're going to simply evaluate that binomial by using FOIL. So we're going to say 3 squared plus 6h plus 8 squared minus 3 squared, and you may have noticed that I didn't actually evaluate 3 squared. I didn't write it as 9 because it actually cancels out down here. So we have this expression here, and now those 3 squares, actually that positive 3 square and the negative 3 square, cancel out. So we're left with 6h plus h squared over h, and the nice thing is that h also cancels out, well, some of the h's. So we're left with 6 plus h. But it's not just 6 plus h. We have to remember what we're asking ourselves. We're asking, what is the limit as h approaches 0 of 6 plus h? So as h approaches 0, what does 6 plus h approach? Well, that's pretty simple. This is a simple limit expression. We can just substitute h as 0, and we'll get 6 plus 0, which is 6. And that is indeed the slope of this tangent line. The slope of the tangent line of at x equals f of x equals x squared at x equals 3 is 6. The slope of this line is 6. That's it. That's what the derivative actually helps us to do. It's nothing but the slope of the tangent line at a specific point on a graph. Now, what we did here is we found the slope of the tangent line at a specific point, x equals 3. Well, we can actually use the derivative to find a general formula to find the slope of any point on this graph. So we can choose any point on this graph, and we can find the slope of the tangent line that touches the graph at that point. All right. So we can use the derivative to find the general formula for the slope of the tangent at any point on the graph. So we have f of x equals to x squared, and we want to calculate the derivative of x squared. So we're saying d over dx of f of x is nothing but the derivative. We want to find the derivative. Is the limit as h approaches 0 of f of x plus h minus f of x over h. Remember, this is nothing but the slope. This is the slope between 2 points on the graph, and we're asking ourselves, what happens as h approaches 0? What happens as these 2 points come closer and closer together? So we know that f of x is equal to x squared, so we can just pop that function right in there. F of x plus h is nothing but x plus h squared, and then we have minus x squared for f of x. So unraveling this binomial, we get x squared plus 2xh plus h squared, and then minus x squared. We can cancel these two terms, and we get 2xh plus h squared over h, and we get 2x plus h finally after we do all our simplifications. Now we're asking ourselves, what is the limit as h approaches 0 of 2x plus h? So as h approaches 0, what does this expression approach? Well, again, it's a simple limit expression. This is a continuous function, so we can just substitute h as 0, and we'll get 2x plus 0, which is 2x. And that is the derivative of the function f of x equals x squared, 2x. Now I've written some problems here. So we want to find the slope of the tangent line at f of x equals x squared at 1. So we want to find the slope of the tangent line at x equals 1. So we can use our derivative. So we found it as 2x. So it's going to be 2 times 1. Our x is 1, so 2 times 1 equals 2. The slope of the tangent line at 2 is going to be 2 times 2 equals 4. The slope of the tangent line at 3 is going to be 2 times 3 equals 6, and so on and so forth. So that is the derivative. It's nothing but the slope of the tangent line at a point in a graph. And there's nothing special about f of x equals x squared. We can actually find the derivative of most functions. So now we're going to go over some rules regarding functions. Regarding the derivatives and how we can actually use these rules to calculate the derivatives of other functions. So here, let's investigate the power rule. All right, so the power rule says that the derivative of a polynomial function, of a simple what is this called? A monomial. So, but yeah, monomial polynomial function. Oh my god, a monomial polynomial. So this is just called a monomial, right? It has one term. So, okay, let's not get ahead of ourselves. The derivative of x to the power of n is equal to n times x to the power of n minus 1. So what we're doing is we're bringing that n, we're taking that n, and we're bringing it to the front. So we have nx, and we're just subtracting 1 from that n. And that's how we get n times x to the power of n minus 1. So that's the power rule right there. And it only works for n where n does not equal to 0. So I have some examples here. Let's say we want to find the derivative of the function x squared, which we actually did in the previous example, the previous page. Well, it's simply we bring the 2 down, so 2x, and then we just subtract 1 from the power. So we get 2x to the power of 2 minus 1, that's just 2x, which is also the result we got on the previous page. I have the derivative of the function x cubed now, and we're going to evaluate the derivative of this. So we bring 3 down, minus 1 from the 3, and we get 3x squared. The same thing for x to the fourth power. Bring the 4 down, minus 1 from the power, and we get 4x cubed. And that's the power rule. It's just a nice and easy way to find the derivative of functions where you have a polynomial or a power or an exponent. Now we're going to look at the derivative of a constant. So the derivative of a constant c is always going to be equal to 0, where c is a constant. And there's actually a pretty simple explanation for this. At its core, the derivative is the slope of the tangent to the graph at any point. So think about a graph with a constant output. So let's say f of x equals 3, or f of x equals pi, or f of x equals 0.001. What would it look like? Well, for any x, it's going to have the same y value. That's what this constant function is telling us. So it's going to be a horizontal line, right? Now, for a horizontal line, if we take any arbitrary points, what is the slope of the tangent line at that point to the graph? What is the slope of that tangent line? Well, it's going to be another horizontal line, right? And it's quite obvious. It's obvious that the tangent to any point on a constant graph is also a horizontal line. And the slope of a horizontal line is 0. Hence, the derivative of a constant is 0. So remember, the derivative is nothing but the slope. Derivative equals slope of a tangent. And the slope of this line is 0. In fact, the slope of any straight line, so let's say I had a straight line like this, right? The derivative of this line is simply the slope, because for a straight line, there is no changing, the rate of change is constant. So the derivative actually will be a constant expression. So let's say this line was y equals 6x. Well, it's not really y equals 6x, but imagine it was y equals 6x. The slope is 6, right? And the derivative is also going to be 6, because that's the slope of the tangent at any point on this graph. All right, so that's the derivative of a constant. So the derivative of a constant is always equal to 0. Let's now go on to the derivative of a times f of x, where a is a constant. So we have a function f of x, and that's not meant to be dy, is it? That's meant to be d dx. Okay, that's a typo there. I'll fix it later, but that's meant to be d dx. Well, d dx of a times a function is equal to a times the derivative of that function. So I got an example here, a simple example. We have f of x is equal to 2x squared. So usually we're used to doing f of x is equal to x squared. But now we're scaling that function by 2. And I want to find the derivative of f of x. So the derivative of f of x is the derivative of 2x squared. So you can think about it, I have x squared here, I have 2x squared here, and I'm applying the derivative operator to both sides. That's what we're doing. So now we're finding the derivative of 2x squared. Using our formula up here, we can see that we have a constant here, or a scalar here, and we have a function here, x squared. So what the formula tells us is that we can take this 2 outside the function. So we can say this is equal to 2 times the derivative of x squared. And we can use the power rule to find the derivative of x squared. We know it, it's 2x, just times it by 2, and we get 4x. That's the derivative of 2x squared. And that's that rule right there, the derivative of a constant times a function. And I have a simple proof here. It's not necessary, but it's a simple proof, so I thought I might as well include it. So I'm trying to find the derivative of a function f of x scaled by some constant a, and I'm going to take the limit. So I'm using my limit formula here. So if you remember the formula for the derivative, the actual concrete formula, is the limit as h approaches 0 of the slope of a secant. So I'm using that same formula here, but the function is a f of x, a times f of x. So I'm just plugging in x plus h and x into this whole argument here, or this whole function. So I'm doing that, and you can see that we have a common factor here, which is a. So we can actually factor out a. So we'll get a times this, and the product of limits, the limit of a product is the product of the limits. That's that's from your basic limit operations. So the limit of this is the same as the limit of as h approaches 0 of a times the limit of h as h approaches 0 of this. And the limit of h as h approaches 0 of a is nothing but a, because a doesn't have any terms relating to h, so it's going to be a. So we have a times the limit as h approaches 0 of this slope. And you can see that this is nothing but the derivative formula. We have extracted the derivative formula. So we can just simplify that as d dx of f of x. And that's how we get the derivative of a f of x is equal to a times the derivative of f of x. So that's the derivative of f of x scaled by some constant. Alrighty, now we have the derivative of h of x, where h of x is a sum of two functions. So we're trying to find the derivative of the sum of two functions. Well, the formula for that is, again, this is meant to be d over dx, not d over dy. So we have the derivative of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. So the derivative of the sum is equal to the sum of the derivatives. Easy and nice. All right, we have an example here. H of x is equal to 6x squared plus 5x. We want to find the derivative of h of x. So we apply the derivative operator to both sides, and we're finding the derivative of 6x squared plus 5x. Now we can see here that these are two separate functions. We can evaluate these as two separate functions. So using the formula up here, we see that the derivative of a sum is equal to the sum of the derivatives. So we just separate out those two functions, and now we can calculate the derivative for these two functions. So using the power rule, we can see that we bring the 2 down, and also using the constant scalar rule, we bring the 2 down, and so it becomes 6 times 2, which is 12, and we minus 1 from the power, which becomes 12x. And we also have here the derivative of a straight line, 5x is a straight line, is nothing but a slope, and that's going to be 5. And I have a proof here. I didn't have enough space, so it actually ends here. So it goes like this, but let's start from the start. So I have h of x is equal to f of x plus g of x, and I'm trying to find the derivative of h of x. So I'm using my standard formula here, except I've replaced h. So before, h referred to our little nudge. So h was that distance between the 2 points. But since I'm using h as the name of the function, I'm actually going to be replacing that distance by delta x. So delta x is that same distance between the 2 points. So h of x plus delta x minus h of x over delta x. It's the same formula, just different symbols. All right, and that's our standard formula here. But remember, h of x is equal to f of x plus g of x. So we can actually substitute that into here. So h of x plus delta x is actually going to be equal to this these two terms here. And that's just plugging this value into these two values, and we're writing it there. And the same thing for h of x here, that's going to be minus f of x minus g of x. Now, I'm just rearranging the terms here. So I'm bringing f of x over here and g of x next to g of x plus delta x. So I have it in order. And we can see that we have a sum here. So we have this, and we have this. So I'm just splitting those two into two fractions. So we have f of x plus delta x minus f of x over delta x, and g of x plus delta x minus g of x over delta x. And we know that the limit of a sum is the sum of the limits. That's basic limit operations. So I've separated these two into the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, plus the limit as delta x approaches 0 of g of x plus delta x minus g of x over delta x. So we have two limit expressions here, and you will notice that this is essentially the formula of the derivative here, the basic derivative for f of x, and this is the formula for the derivative of g of x. So this is this, and this is this. And you can see that we found that if h of x is equal to f of x plus g of x, and we want to find the derivative of h of x, it's nothing but the derivative of the two functions of which h of x is a sum. So that's the derivative of a sum. Let me just show you that formula one last time. There's the formula. Alrighty. So I have two practice problems here, which I'm going to solve right now. So we have f of x is equal to 2x cubed minus 9x squared plus 5x minus 16. And I want to find the derivative of f, or f prime of x. So let's do that. So we can see we have a lot of different terms here, and using the rule we just learned in the previous page, we know that the derivative of a sum is equal to the sum of its derivatives. So let's say d over dx of f of x is equal to d over dx. Oh my god. All right, there we go. Of 2x cubed minus d over dx of 9x squared plus d over dx of 5x minus d over dx of 16. All right, now we can evaluate these individual derivatives. So we can use the power rule to evaluate this. So just bring 3 down, that becomes 3 times 2, which is 6. And then minus 1 from the 3, that becomes x squared. Minus, using the same power rule, we can see that this is 18x. And then we have the derivative of a straight line, and we have the slope here is 5. That's going to be plus 5. And we have minus 16, so the derivative of constant is 0, so we don't have to worry about that. It can be plus or minus 0. So that's the final derivative formula. All right, let's do the next one. G of x is equal to 1 over x cubed minus, now this might look like a complex expression, but we can formulate it into exponents, and we can use the power rule to actually break this down. So we want to find the derivative of g of x. So let's see, d over d of x of g of x is equal to, all right, actually before we do that, let's simplify g of x. So we have g of x is equal to 1 over x cubed minus 7 over, so we have, this is going to be the square root of x to the power of 5. Now 1 over x cubed, that's the same thing as x to the power of minus 3. And then this is going to be 7 times 1 over x to the power of 5 squared. We can simplify this even more, so let's just rewrite that. So x to the power of 5, square root of that is nothing but x to the power of 5 over 2. And then we have 1 over x to the power of 5 over 2. So the reciprocal means we just add a minus sign to the exponent. So this is going to be equal to x power of minus 3 minus 7 times x to the power of minus 5 over 2. All right, let's just simplify. X minus 3 minus 7x to the power of minus 5 over 2. All right, now we can evaluate the derivative of this. So g prime of x is equal to, using the power rule, we just take the power, bring it down. So that's going to be minus 3x. And then we subtract 1 from the exponent, and we get minus 4. Now for the second one, we'll do minus. And remember, we're also using the sum formula. So the derivative of a sum is equal to the sum of its derivatives. So we just evaluate the derivative of each of these. Now we'll get the derivative of the whole function. All right, so minus 7x to the power of minus 5 over 2. We just bring the minus 5 over 2 down. So it's going to be, let's put some brackets. So 7 bracket, bring that minus 5 over 2 down, bracket, and then we have x, and we just subtract 1 from that exponent. So negative 5 over 2 minus 1 is going to be negative 5 over 2 minus 2 over 2, which is negative 7 over 2. And now all we need to do, we just need to evaluate all these terms. So minus 7 times minus 5 over 2 is going to be positive. So plus 7 times 5, 35, 35 over 2. Then we have x to the power negative 7 over 2. And that is the derivative. So we had our function 1 over x cubed minus 7 over the square root of x to the power of 5. And we found the derivative. And it's actually pretty amazing. We have this abstract function here, this weird looking function. And we were able to find a formula that actually gives us the slope of the tangent line at any point on that graph. And yeah, that's it. That's derivatives in a nutshell, and some of the basic rules that you can apply to derivatives. In the next video, I'm probably going to go over things like the chain rule and the product rule, which I haven't actually learned yet. So once I learn those, I'm going to make a video about it. And yeah, that's derivative for you guys and for my future self as well. So thank you for watching.